Carlos Plain, a professor from Durham School, shares that throughout his lifetime, he focused on developing a precise and well-defined theory of the universe he now observes. As this hypothesis is put to the test, something he welcomes, recognizing that science advances through such challenges, the James Webb Space Telescope is revolutionizing and challenging many long-established concepts in cosmology. Revealing an entirely new view of the cosmos as we enter the new year, the telescope's ultra-deep field image has shown that there are significant errors in our previous understanding of the universe. Initially designed to uncover the first stars of the universe, this telescope is evolving into a challenger to past ideas and may bring about an entirely new approach to cosmology. However, not all scientists are afraid of these revelations. Many experts in the field embrace these changes because it had become increasingly evident that something was amiss with the older theories. The consistency in calculating the universe's expansion rate should have raised doubts about earlier perceptions, but for a long time, experts held on to old assumptions. The cosmic microwave background, CMB, regarded as the oldest light in the universe, originated about 380,000 years post-Big Bang, when the universe cooled enough for protons and electrons to bond and create stable hydrogen atoms. This period, known as rayonization, allowed the universe to become transparent to light. In 1964, American physicists Arno Penzias and Robert Wilson made a breakthrough discovery while working with new radio antenna technology. They detected the CMB. This finding was long considered one of the strongest pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and securing their place in the history of astronomy. The CMB offered scientists a unique look at the early universe, revealing small temperature fluctuations that helped provide insights into the conditions that followed the Big Bang. The CMB was also used to test the expansion rate of the universe and verify other cosmological assumptions. As early as the 1920s, astronomer Edwin Hubble had established that galaxies in the far distance were moving away from us, with their speed correlating to their distance. This observation led to what is now called Hubble's law, or the Hubble constant. While Hubble did not have the advanced observational tools available today, his discovery, alongside the later finding of the CMB, led to recalculations of the universe's expansion rate, which turned out to be slower than Hubble's original estimate. Later, astronomers used Type ER supernovae, known as standard candles due to their consistent luminosity, as reliable measurement points to gauge cosmic distances. These recalculations, based on the CMB, suggested an expansion rate of approximately 67 km per second per megaparsec. Measurements from supernovae indicated a higher rate of around 74 km per second per megaparsec. The divergence in these calculations has been a point of contention for scientists for decades, with many researchers realizing that something was fundamentally wrong with how the CMB and the expansion rate of the universe were being interpreted. This inconsistency, known as the Hubble strain or SAR anomaly, suggests that there are flaws in our basic understanding of the cosmos. These discrepancies have profound implications, challenging our most fundamental beliefs about how the universe works. The issue has been known since the 1990s, when scientists began to suspect that there were errors in the methods used to measure the CMB or perhaps even in the assumptions made about the universe's expansion over time. The discrepancy between observed and predicted expansion rates became increasingly apparent. The Hubble strain suggests that our theories may need a drastic overhaul, indicating that key elements of our cosmological model could be deeply flawed. Now, with the advent of the James Webb Space Telescope, researchers are gaining extraordinary new data that may help resolve the issues with our understanding of the universe's expansion rate. These new findings are so profound that they could shake the very foundation of our previous cosmological theories. The telescope is revealing galaxies and systems so ancient and evolved, that they suggest the universe's evolution could have begun well before the Big Bang. This challenges the old cosmological views, forcing scientists to reconsider the nature of the Big Bang and the expansion of the universe itself. Instead of merely talking about errors or discrepancies in data, scientists are now addressing what many describe as a crisis in current cosmological models. It's no longer just about miscalculations, it's about rethinking our very conception of the universe. The new data from the James Webb Space Telescope reveals a cosmos far more surprising than anything previously imagined. The Hubble strain, once a source of confusion for those holding on to traditional theories, is now a focal point for scientists who must confront the possibility that our understanding of the universe might need to be completely redefined. As scientists continue to investigate these unprecedented discoveries, they are also confronting the larger question: do we truly understand the universe? To answer this, it's important to grasp how science operates. Cosmologists employ intricate mathematical models, careful analysis of data, and logical reasoning to make predictions and test hypotheses. Their conclusions are based on a combination of empirical evidence, well-established principles, and theoretical calculations. However, it's important to remember that science is a dynamic field, and theories are always subject to change as new data comes to light. The term hypothesis itself suggests that scientific understanding is an ongoing process of refinement, not an absolute truth. One of the most critical sources of data for cosmologists is the light captured by telescopes, as well as the radiation and sound waves detected through radio telescopes. More recently, neutrino detectors and gravitational wave observatories have added to our understanding of the cosmos. The James Webb Space Telescope provides an invaluable tool for studying the earliest galaxies, their structure, mass, and the number of stars they contain. It can also trace the formation and evolution of galaxies over time. However, Webb is not without its limitations. For example, it's sometimes difficult to distinguish between distant galaxies and massive black holes that emit similar levels of brightness. This realization forces us to acknowledge that for a long time, science may have accepted certain assumptions as facts, dismissing other plausible explanations. The recent revelations from the James Webb Space Telescope underscore the importance of remaining open to new ideas and theories. The data gathered by Webb presents a critical opportunity to replace outdated models with fresh perspectives, much like how science has historically evolved through groundbreaking discoveries. As scientists continue to unravel the mysteries of the cosmos, they are faced with the challenge of developing new explanations for what they are finding. These discoveries are causing significant shifts in the foundational concepts of our understanding of space, prompting a reassessment of our knowledge of cosmic expansion, and the forces at work in the universe. Our current models of physics and astronomy are still largely rooted in the 17th-century laws of Isaac Newton. While his laws of motion and gravity have served as the cornerstone of our understanding of physics on Earth, they were eventually found to require modification when applied to space. This led to Albert Einstein's groundbreaking work in the early 20th century, particularly his special theory of relativity in 1905, which revolutionized how we perceive space, time, and motion. Einstein's general theory of relativity, published in 1915, ended this revolutionary thinking, proposing a mathematical model that explains the gravitational effects of massive objects on the curvature of space-time. While Einstein's theories were crucial in transforming our understanding of the universe, he himself acknowledged their limitations. He believed his theories would never fully account for all the complexities of the cosmos and yearned for a unified theory that would tie together all of physics. Yet no scientist has succeeded in achieving this comprehensive model of the universe. It remains an open question: what might this theory look like, and could it win someone a Nobel Prize? Among the leading suspects for the current cosmological crisis are dark matter and dark energy. These concepts, which make up about 95% of the universe, remain largely theoretical since neither has been directly observed. While these mysterious substances are integral to current models of the universe, their precise nature is still unknown. Some researchers speculate that they might not exist in the ways we assume, requiring alternative explanations for the observed expansion of the universe and the dynamics of galaxies. Others suggest that dark matter and dark energy may have evolved over time, altering their properties in ways we don't yet understand. Another possible explanation involves gravity, a force that we know causes attraction between masses. Yet even this force, which has been described by Einstein's theories of relativity, remains an area of ongoing study. Scientists are exploring the possibility that gravity might have characteristics that we don't fully comprehend, or that a different unknown force could be responsible for the gravitational interactions we observe. As the field of cosmology continues to evolve, scientists are revisiting some of the constants that have long been assumed to govern the universe. Cosmology, after all, is an ever-developing field driven by humanity's unceasing pursuit of knowledge. From the early observations of the night sky by ancient civilizations to the modern instruments we use today, each step in our journey to understand the universe has led to new mysteries and insights that challenge what we once thought we knew. The James Webb Space Telescope stands as a symbol of our progress in space science, offering unprecedented abilities to explore the universe's beginnings and the evolution of galaxies. Launched with remarkable capabilities, Webb represents a leap forward in observational astronomy, enabling us to examine radiation from the early universe with unparalleled precision. Its discoveries have the potential to reshape how we view cosmic origins and evolution. As scientists continue to study these findings, they face a fundamental question: what is our true understanding of the universe? With Webb's data, we now have an opportunity to replace outdated models and expand our knowledge in ways previously unimaginable. The mysteries of the universe, from the Big Bang to the unknowns of dark matter and dark energy, are becoming clearer with every discovery. The future of cosmology promises to be filled with groundbreaking revelations that will undoubtedly challenge our most established theories. Science, much like the universe itself, is always expanding, driven by the quest for knowledge and the wonder of discovery. The James Webb Space Telescope, at the forefront of this ongoing journey, is guiding us toward new horizons, bringing us closer to answering the ultimate questions of existence: how did the universe begin? What is its fate? And are we alone in this vast cosmos? These questions are as old as human curiosity, and with each new observation, the answers become ever closer to being revealed.